This lecture, I want to talk about what's called alternating series. For the moment, in this lecture, we're going to assume that the A numbers, A1, A2, A3, and so on, are all positive. And what we mean by an alternating series is one of two things. Either A1 minus A2 plus A3 minus A4, and so on and so forth, or negative of A1 plus A2 minus A3 plus A4 minus A5, and so on. If we want to write these in sigma notation, both of them are almost the sum n equal 1 to infinity an, but I need to put in an extra factor that will be either 1 or negative 1 as appropriate. The second type is the negative of the first type. So in much of my discussion, I'll worry only about the first type because that tells me all about the second type as well. To be a little bit more explicit about it, if you include only the first term, in the first type you would have A1, and in the second type you would have the negative of A1. For the n equal 2, you would have A1 minus A2 versus negative A1 plus A2. And as you can clearly see, all of the partial sums for a type 1 series are the negatives of partial sums of an alternating series of type 2. So if these things converge to a certain number, say S, then these things converge also to negative S. If one converges, the other converges as well. As a concrete example, think of 1 minus 1/2 plus 1/3 minus 1/4, and so on and so forth. In sigma notation, you could write this as the sum n equal 1 to infinity of the n plus first power of negative 1 over n. We don't know if that converges or if it diverges at the moment. We have no way at all of dealing with it yet. This one, though, the second one is also an alternating series. 3 minus 4 plus 5 minus 6 plus 7. This is the sum n equal 1 to infinity, negative 1 to the n plus 1 power, multiplied by the number n plus 2. The second one clearly does not converge because any convergent series has to have terms that tend to 0, and negative 1 to the n plus 1 times n plus 2 doesn't tend to 0 as n tends to infinity. If we have an alternating series, though, there's special structure to it. Suppose I have one of these alternating series and the positive numbers an get smaller as you increase the index, and also the individual numbers an tend to 0 as n tends to infinity. As we're going to see, in the case of an alternating series, that is enough to guarantee that the series converges. As we'll see a little bit later, we get an extra bonus too. This is going to tell me how closely a given partial sum approximates the true value of the alternating series. To see why this is true is a little bit tricky, but not very tricky. Imagine that you have partial sum number 1, S1. S1 is just A1, which is positive because all of the A numbers are positive. When I calculate S number 2, I'm going to calculate A1 minus A2, which is going to be located at a location that is smaller than S1 by an amount A2. The key thing to recognize, though, is A2 isn't as big as A1 is because of the decreasing part. So I started off sitting at A1. I move A2 units of distance to the left, but that's not enough to move me all the way to 0. So S2 has to be positive. Also, S2 has to be smaller than S1. But this is an alternating series, so things are more complicated than this. If I want to calculate S number 3, that would be A1 minus A2 plus A3. S2 is A1 minus A2. So when I add the A3 to obtain S number 3, that's going to move me to the right of the location of S2 by an amount A3. But you see, A3 is smaller than A2 was. And if I wanted to get all the way back to the location of S1, I would need to add A2. So S number 3 is bigger than S number 2, but it's not as big as S number 1 was. Make sure you've got this straight in your head because we're going to generalize it in a second. If you keep doing that argument, you find out that S2 is smaller than S1, S3 is bigger than S2, S4 is bigger than S3, S5 is bigger than S4, S6 is less than S5, and so on, and so on, and so on. We were hoping maybe for some sort of monotone behavior, but it's all jumbled up. It turns out we'll be able to unjumble it though. If I draw this same picture in, except I only draw in the even indexed partial sums, S2, S4, S6, and so on, you see that you get an increasing sequence of numbers. Not only that, each one of these numbers is bounded. All of the S numbers are between 0 and A1. In particular, the even indexed ones are. So this means the set of even indexed partial sums are bounded and increasing. And one of the things we convinced ourselves of earlier is that if you have any sequence of numbers that's monotone and bounded, that sequence converges. So the even indexed partial sums, just looking at those numbers, they converge to something that I'm going to call capital E, which is short for even. At the top, we have that same picture that we figured out in general, but in the middle of the page, I'm only going to draw in the odd indexed partial sums. S1 was here, S3, S5, S7. As the index increases, the odd indexed partial sums are monotone, except they're monotone decreasing instead of increasing. But even so, all partial sums lie between 0 and A1, so the sequence of odd indexed partial sums is monotone and bounded, and that means that that sequence of numbers converges. I'll call the thing that it converges to script O. Script O is short for odd indexes. Now, any partial sum of the alternating series is either an odd indexed partial sum or an even indexed partial sum. So what could go wrong? It's conceivable that the even indexed partial sums, which are increasing and bounded, converge to some number E, and that the odd indexed partial sums, which are decreasing and bounded, converge to some number script O, and they're not the same number. That would tell me that there's not one single number that all partial sums look like as the indexes become very big. And technically speaking, that would say our alternating series doesn't converge, even though it's composed of two subsequences that do converge. So if E is not equal to script O, then the infinite series in question diverges. If you take the logical contrapositive of this, if the series converges, then E does have to equal script O. But see, this is not what we want exactly. What we want is some easily checkable condition that says if something happens, then you get convergence. We want something that's actually going to tell us something. Because of the relationship between even and odd partial sums, though, that's not going to be very hard to do. I'm going to think of having partial sum sk, which is a1 minus a2 out to, I'll say that it's plus ak because it doesn't make any difference. If sk is like this, then sk plus 1 would be the same sum, except you would be subtracting away a number k plus 1. Now, listen to this logic carefully. If k is even, k plus 1 is odd. If k plus 1 is even, k is odd. So if I subtract these two things, I'm going to be subtracting away two partial sums that differ in index by only 1. One of these things is going to be an even indexed partial sum, and the other one's going to be an odd indexed partial sum. To get rid of all the plus or minus ambiguity, I'll take the absolute value. This says that the distance between partial sum number k plus 1 and partial sum number k is exactly a number k plus 1. If k is even, k plus 1 is odd. If k is odd, k plus 1 is even. E minus O in absolute value is the same as O minus E in absolute value. So as I was saying, it doesn't make any difference. Take the limit of this formula as k tends to infinity. On the right, you'll have the limit of the individual terms, and over here, say the k plus 1 is even, because which one is which doesn't matter. The limit as k tends to infinity of sk plus 1 is E, minus the limit as k tends to infinity of sk, which would be O. What is it that we want? We don't want there to be any gap between E and O on the number line. The distance between E and O is the limit of the individual terms. So what circumstances lead you to the conclusion that E equals script O? The limit of the individual terms has to tend to 0. Now, sometimes people get very concerned that there's a k here and a k plus 1 there. It's irrelevant. What this says is, as you let the index get big, the individual terms approach 0. So rather than make a big deal out of the k versus k plus 1, I'm just going to write the condition this way. In an alternating series where the ANs are positive, the ANs are decreasing. They get smaller as you make the index bigger. And if the limit of the individual terms is 0, we can conclude that the infinite series that we're talking about converges, because We know the even-indexed partial sums converge. We know the odd partial sums converge. And if this is true, that's equivalent to saying capital E equals script capital O, and there's no gap between the two subsequences. As an example, think of 1 minus 1/2 plus 1/3 minus 1/4 plus 1/5, and so on and so forth. You can write that in sigma notation if you feel like it. The positive numbers involved are an equal 1 over n. Obviously, all of those are positive. Also, obviously, they're decreasing because if I make the number on the bottom of the fraction bigger, I make the fraction smaller. And also, it should be obvious that the limit of the individual terms, the limit as n tends to infinity, 1 over n, is 0. By all of this alternating series stuff we've been talking about, this infinite series converges. It's interesting to note, if you didn't have the minuses, if they were all pluses, if it was 1 plus 1/2 plus 1/3 plus 1/4 and so on, that would be the harmonic series. We've seen at least a couple of different ways that that series diverges, but somehow alternating signs back and forth on the terms as you go along is enough to fix that up. And this series, the alternating series version of the harmonic series, does not diverge, it converges instead. Now, at the moment, we have no clue what that converges to, but it converges to something. Let's look at the sum n equal 1 to infinity, negative 1 raised to the n plus 1 power, n plus 1 over n. The individual terms are positive. If you use the f of x trick, you find out that the derivative is always negative. So my a sub n's are positive and decreasing, but we've got a problem now. The limit as n tends to infinity of an is 1. It's a truism not only for alternating series, but any kind of infinite series. If the individual terms don't tend to 0, then the series does not converge. So this tells me right away the series diverges. In view of what we've said before, though, the even index partial sums converge to something, and the odd indexed partial sums converge to something also. If you remember where this limit came from, it was the limit of, on one side, sk plus 1 minus sk in absolute value, and one of the terms out of the series on the other one. If the individual terms of the series tend to 1, that means the absolute value of e minus script o must be 1. What's going to happen here is the even index series converges, the odd index thing converges to something else, and the distance between these two things is going to be 1. I decided to be lazy, so I wrote a computer program that will add up any number of terms of the series that I feel like telling it to. And then I decided to tell it to add up 10,000 terms. And then I ran it again and told it to add up 10,001 terms. In view of what we've seen here, roughly speaking, we ought to get numbers that are different by about 1. I say about because n equal 10,000 is not exactly the same thing as n tending to infinity. So it's a rough approximation. So S number 10,000, is 0.693071830599310 using double precision arithmetic. S number 10,001 works out to be 1.693197. The 6, 9, and 3 are the same thing. If you subtract S number 10,001 minus S number 10,000, what you get back is 1.003 and some other numbers. It's practically 1, and that's what we said we expected to happen. I could probably make these digits agree more if I did more than 10,000 and 10,001 terms, but I think this is enough to show you what I mean here. For alternating series, though, we can squeeze some more information out of this. Suppose that you calculate partial sum number k. When you calculate partial sum number k plus 1, you are either adding or subtracting a number k plus 1. Just for convenience, I'll look at the case where I add. The case where you subtract works exactly the same way. So I'm going to take S number k and increase it by a certain amount to get S number k plus 1. The amount that I increased it by is a number k plus 1. To get S number k plus 2, I'm going to subtract a2 away. That'll mean S number k plus 2 is smaller than S number k plus 1. But see, a2 isn't as big as, ak plus 2 isn't as big as ak plus 1 is. So even though I'm moving to the left, I can't move all the way back to sk. So S number k plus 2 is going to be bigger than sk. When you calculate S number k plus 3, you'll add a3, so you'll move a3 units of distance to the right, which isn't as big as a2, so you don't end up back here at the far right again, and so on and so forth. If I calculate S number k, all SNs within k plus 1 or bigger are going to be trapped between sk and sk plus 1. But the distance between sk and sk plus 1, you'll remember, is ak plus 1. So if you have one of these convergent alternating series and you calculate S number k, the difference between S number k and the actual value of the infinite series can't be any bigger than a number k plus 1, the next number that you would have added or subtracted in order to get sk plus 1. This is going to let me get really easy estimates for how accurate certain calculations are. So for example, suppose I had the infinite series sum n equal 1 to infinity, negative 1 to the n plus 1 times 1 over n to the 5 power. Suppose that you calculated S number 7, which is this quantity. I'm not going to bother writing that out as a decimal because I'll do that in some upcoming examples. A perfectly reasonable question for a person to ask themselves is, how different is the value of this partial sum from the true value of the infinite series? And because of what we just said a minute ago, the answer is by no more than the next term you would have added in to get the next partial sum, no more than 1 over 8 raised to the 5 power, which according to my calculator is about 0.0000305. If you add up and get S7, then roughly your answer is going to be right to about 4 or 5 places after the decimal point. That tells me how accurate it's going to be. Things don't always work out so nicely. One sum that we looked at earlier in this discussion is the sum n equal 1 to infinity, negative 1 to the n plus 1 power over n. We showed that that converges. Suppose that you calculated partial sum number 10. I want to figure out how different the value that you get is going to be from the true value of the infinite series. The answer, by no more than how big the next term that you would have added in. The terms, the a numbers, without the minus 1 powers, is 1 over n. So your error can be no more than 1 over n with n equal 11. The error is no more than 0.09 some odd. That's not very good. It's not helpful. It doesn't say that by doing that, I'd get an extremely accurate estimate for the true value of the infinite series. So turn this around backwards. How many terms are needed to make Sk within 0.000001 of the infinite series? I should have written k here instead of n. The next term, I should have written 1 over k plus 1, but I wrote 1 over n plus 1, so we'll go with that. I want 1 over n plus 1 to be smaller than 1 millionth. Multiply both sides by n plus 1, divide both sides by 1 millionth, subtract 1, and you'll find out that n has to be at least 999,999. This is informative, but in a bad way. This tells me that if I want to approximate the value of this infinite series by a partial sum, I'm going to need a huge amount of terms to do it. It's probably not practical to do that, at least not without a computer. At one time, I thought you pronounced these kind of things by saying 0 real loud or 3 real loud, but that's not the case. You pronounce this as 0 factorial, 1 factorial, and so on. For purposes of convenience, we define 0 factorial to be 1. 1 factorial is also 1. 2 factorial is 2 times 1. 3 factorial is 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. And in general, n factorial is n times the factorial of n minus 1. These kind of numbers come up in a very large number of situations, from statistics to physics to infinite series, which is what we're interested in right now. So if you've never seen these numbers before, we need to become familiar with them. Also, you can calculate these numbers on your calculator if you want to, and I feel like I should show you that. So suppose that I wanted to calculate 10 factorial. I would type in the 10, I would push the math button, go sideways to probability. On this calculator, the 4 has the exclamation point to go with it. So I'll type a 4. 10 factorial is 3,628,800. If you want to calculate 15 factorial, 15 math, sideways to probability, choice number 4, and enter. And you can see it's gone kind of funny looking on you. This means 1.307 times 10 to the 12 power. This is roughly 1.3 trillion. So as the n gets bigger, the n factorial gets big really, really quickly. And as I said, you'll see these kind of numbers in a wide variety of applications. So it doesn't hurt us any to see them here. think about the infinite series. The sum, n equal 1 to infinity, -1 to the n plus 1 over not n this time, but n factorial. N factorial is always at least as big as n. So these a numbers that I'm looking at, the 1 over n factorial, are smaller than the 1 over n's are. The 1 over n's tend to 0 as n tends to infinity. So 1 over n factorial also tends to 0. It's not difficult to see that 1 over n factorial is decreasing with n. And obviously 1 over n factorial is positive. So because of the alternating series test that we've developed, we know that this series converges. Suppose I calculate S number 9, and I want to be real clear about this. That means I'm going to go out here until I've got 9 terms, which means n will go out to n equal 9. How different is that from the sum n equal 1 to infinity, -1 to the n plus 1 over n factorial? The answer is by no more than a number 10, a being 1 over n factorial, no more than 1 over 10 factorial, S number 9, partial sum number 9 for this series is very close to the true value of the infinite series. And again, I haven't worked the partial sum out because I'll do one of those in a moment. Actually, I had forgotten that I did work out the partial sum. Using a calculator, the partial sum works out to be 0.6321208113. I have underlined 7 digits after the decimal. Now, you have no reason to believe me at the moment, but the true value of this infinite series turns out to be 1 minus 1 over e. We'll talk about where I got that when we talk about power series. The true value of the infinite series is 0.6321205588, and in the exact value for S, there's a 5 in that location. In S number 9, there was an 8. So you see, I am getting about the right number of decimal places here. Where I'm getting this from should be a complete mystery to you right now. I want to look at another one of these. I want to look at the sum n equals 0 to infinity, -1 to the n power over 2n factorial. 2 times 0 is 0, 0 factorial is 1, -1 to the 0 power is 1. So my initial term is going to be 1. I want to look at S number 5, and I want to be very clear on what I'm talking about here. In this index sum here, I want n equal to 0, 1, 2, 3, 4, and 5 to show up as values for the n. That means on the bottom, the last term that I'm going to be putting in is going to have 2 times 5 factorial, 10 factorial in it. So if I write out all the terms up to and including the 1 over 10 factorial, this is what I mean by S number 5. I got my calculator out, I calculated all of the factorials, did the arithmetic. S number 5 is 0.540302338. The next term, if I wanted to add in the next term to get the S6, then the last term would be having 2 times 6 factorial on the bottom, 12 factorial. The error, the difference between the true value and partial sum number 5 is no more than 1 over 12 factorial, which works out to be 0.000 0, 0, 0, 0, 0, 209. So I'm going to mark off the 9th decimal place here. Now, it turns out that the actual value of this infinite series is cosine of 1 radian. This is another thing you have no reason to believe me on right here, but it turns out to be true. I set my calculator in radian mode and calculated cosine of 1 and got 0.54030230, which you'll notice is the same digits that was in S number 5. And then the one after that represents the first digits where they could be different. And in one, I get a 3, and the other, I get a 5. S number 5 here is an extremely accurate estimate for cosine of 1 radian. Returning to that alternating version of the harmonic series, we've already decided this series converges, but as it turned out, it converged very slowly. If I want to compute Sk so that the difference between Sk and the true value of the series is no more than 0.0000001, we figured out that we need at least 999,999 terms to actually do that. I wrote myself a little program to do the calculation for me. Partial sum number S999999 is 0.693147680560252255. You may be asking yourself, why did I write all those digits down? Because I'm interested in seeing when this becomes different from what it's supposed to be equal to. You have no reason to believe this statement, but the value of this infinite series is actually natural log of 2. So if I write out the natural log of 2 in decimal, 0.693147180559, and if you look at it in the 7th decimal place is where my partial sum and the exact value of natural log of 2 start being different. So the difference between my partial sum and natural log of 2 is about 5 times 10 to the negative 7 power, which is certainly smaller than this. The reason that this is natural log of 2 is going to take a little explaining. The way we decide whether things that are alternating series converge or not is comparatively easy, and even getting the error estimate for how wrong you are is fairly easy. We'll talk more about this as we go along. In the next discussion, we're going to look at the concept of absolute convergence and why it's a worthwhile thing to know about.